Okay, let's start my second talk on photoacoustic signals analysis and imaging. Today we will first discuss about single cell photoacoustic signal calculation and its spectrum, single cell shape dependent PA signal, and angular distribution of differential photoacoustic cross section, and then we will move to photoacoustic microscopy and tomography. Okay, basically mathematically, as I said yesterday, you can solve the differential equation, wave equation, basically that is the Helmholtz equation, time independent wave equation. For a spherical source, you can easily solve that and use the boundary condition, that is the continuity of the pressure and the particle velocity, and you can get a solution. And if you take the Fourier transformation of this solution, you will get the time domain signal. So we solve the wave equation in the frequency domain, and then we use the Fourier transformation to get the time domain signal. And if we calculate this expression, we will get this type of signal. This is the one of the very important paper published by Gerard Diebold in Physical Review Letters. And so this is the typical N-shaped pulse that we expect, or that this is a very well-known signal that we get in photoacoustics. If you have a spherical absorber or spherical source, if you have a detector anywhere in the any angular direction, you will get a N-shaped pulse. And so and the and the width of this pulse, that is, this is the x-axis is t. If you multiply this, the width of the pulse with the velocity of sound, then you will get distance, and this distance will be equal to the diameter of that absorber. This is very well known relationship that people know. So, and you see that this is a very sharp pulse because it has edges, and so these are the theoretical signals calculated using this equation, and these are the experimental signals that he measured in 1991 from a single fluid sphere containing CCl4 and other organic solution. So yeah, this is the main the message from this slide is that if you have a single absorber, it will emit N-shaped signal, and width of the N-shaped signal is equal to the diameter of the source. And if you take the Fourier transform of this signal, you will get this type of spectrum. You can plot this thing. This may be a log scale, or this is a linear scale. You will see that basically it's a spherical Bessel function type of plot, and these are the minimas. These are important from the point of view of determination of size, because the locations of this minima depends upon the size of the object. So once you know these locations, you can tell what is the size of the object. So the idea is you get the signal, do the FFT, get the minima, and then you estimate what would be the size. And these are the for three different sources. That means we have three different signals, and these are the three different spectra, and you can see that almost the minima positions are same, although the composition of the absorbers are different, but actually these locations are dictated by the size of the object.
So here also the side lobes are something undesired, or they are inherent to the, I mean, is it, do we ideally desire only the main lobe, or and just like we have in the previous case, we ideally would not want the side lobe. So here also is that the case?
Okay, in case of ultrasound, right?
Yeah.
But in case of ultrasound, your detector produces a side lobe which is not desirable. But in this case, it is the source that, so you don't have control over that. So,
sorry, just so do you think the width of the lobes is same?
no, they will be, you know, the Bessel function.
Right. So the reason I said is, so maybe then if you have multiple zeros, maybe you can get a better estimate of your.
Exactly,
size.
exactly. That will give you more accurate.
It might be desirable if you right.
Your prediction will be improved if you have this type of spectrum. Okay, so people started to work, use photoacoustic technique to assess cellular morphology. If you have a red blood cell, what is the size and shape, thickness, what is the size and shape of the cells, people started to characterize. So in this context, we will talk little, we have done some work that I will show you. So for example, this is the geometry. So it's not a previous equation. The equation I showed you, this is for a spherical absorber. That means you can solve your differential equation analytically and you can get a solution for that. But if you have a geometry like this, which is not regular, then you have to employ other techniques to solve this equation. That is the main photoacoustic wave equation. In this case, we used a Green's function method to solve this. So your solution becomes this, where A is this, these are the parameters, and G is the Green's function that is known as free space Green's function. So you have to, instead of solving differential equation, you have to solve this integral equation, and you can easily either you do this thing analytically or you can do this thing numerically. So this is, assume that this is a cell, light is coming from here and you have a detector here. So your cell is about 5 micron. Yesterday I showed that there are two conditions we need to achieve, that is the thermal confinement and stress confinement. So your pulse width should be very small. And in this case, people are using picosecond lasers, and your ultrasound signal should contain features in the very high frequency range. That's why people are using 400 megahertz, which is huge, and that's why you don't expect that your penetration will be very limited. Your penetration will be few micrometers. So it is known as photoacoustic microscopy with ultra high ultrasound transducers. Okay, so we generated some red blood cell shapes. Actually, this is the normal red blood cell. It is the biconcave shape, but there are several pathological conditions where your RBC will change, will deform. This is known as stomatocyte, and this is not a good shape from the circulation point of view, because it will create a lot of circulatory disorders. And there is another shape known as stomatocyte and echinocyte, right? Okay, this will have some horns on the red blood cells. So you can produce this type of cells by manipulating the solution. So RBC, if you change the saline water concentration of the salt, it will start to deform. And people started to measure we propose that we can measure the signals from this type of shapes. Then what type of signal we expect or what we will get. We have seen that this is from a discocyte. If you measure from here, that is the theta equals to 0 degree, and if you measure from here, that is the theta equals to 9 pi by 2, and you will see this type of signals. That means your thickness is more, that's why the M-shaped pulse got broadened, and thickness along this direction is really small, and that's why your M-shaped pulse is very narrow. And if you these are the signals for other two shapes, and this is for a sphere. So from anywhere you will receive the signal, you will get the same signal. So these are the things, and so you can see that the signals are different if you probe from different angular locations. And if you plot them, you will get that your first minimum is appearing here. It is about 620 megahertz for a disco cycle if you probe from 0 degree angle. But in this case, it will appear much earlier, around 220 megahertz if you probe from 90 degree angle. And for other shapes, this is for a sphere. So spheres, the spectra are exactly same. These are for stomatocyte 1 and stomatocyte 2, where you can see that the first minimum is appearing slightly earlier than the normal RBC. So in this way, you can characterize you have a time domain signal, and then you do the FFT, get the spectrum, and study the locations of those minimum position. You can, in that way, you can have some idea about the pathology of the cell. This may become important. For example, in case of sickle cell anemia, your red blood cell, they get deformed significantly. So your spectrum will be different. But so if you have a flow cytometric arrangement, cell will go and you can measure the photoacoustic signals and characterize the spectrum. You can see, you can study what is going on, what is the health of those cells. Okay, in this context, we theoretically generated RBC shapes. There are several models. For example, Evans-Fung model. Recently, we used Cassini ovals to generate RBC shape. So this is a theoretical expression, and there are C0, C1, C2, free parameters are there, and if you know the thickness, this is known as dimple thickness. This is the maximum height of a RBC, and this is the diameter of an RBC, and this is small d is equal to the distance between, or if you draw a contour through the maximum height, and this is the diameter of that circle. If you insert those values, you will get what are the C0, C1, C2, and in that way you can generate the RBC shape. And now we can slightly deform, that you assume this half upper hemisphere still retains this shape, but thickness these values have changed, but this half becomes a sphere. So in that way you manipulate the shape, and in this case, for example, this dimple thickness is very small, and you can study what would be the PA signal and what would be the spectral characteristic. And people are also in some literature, we have proposed this thing that you can fit this contour using a Legendre polynomial expansion. Actually, Legendre polynomials are basis functions. They are orthonormal functions. So any arbitrary functions between 0 to pi can be written in terms of this, and if you do this fitting, you will generate this. And so you see that you have only alphas are the coefficients that you can obtain from this fitting, and this is the plot of alpha values for different shapes. This is known as medical image analysis. So you fitting with this type of function, you can get only alpha parameters. So this will reduce your, actually these are the feature extraction type of this. And these alpha values, if you know the alpha values, you can reconstruct what will be the size and shape. Okay, so and this is the method. You have angular radial distance at different angular locations, and this is the Legendre polynomials, and you go up to, in this case we have gone up to if you see that this is a infinite series, but people have shown that if you take summation up to 98 term, that will give you accurate estimation. So we took our L capital L was equal to 19. So we solved these linear equations and then we obtained our alpha values that we have plotted in the earlier slide. Here is the plot. So I already explained this slide that for different shapes, and you are probing from two angles, theta equals to 0 and theta equals to pi by 2. You have different signals and their spectral characteristics are different, and using those characteristics or you can estimate RBC size and shape. People are doing experiment as well. So as I said, they are using 400 megahertz transducer and 300 picosecond lasers to do that. Okay, so then we also estimated what would be the angular distribution of differential scattering photoacoustic cross section. Yesterday I defined this quantity. Actually, people in the ultrasound scattering, optical scattering, this is a very well known parameter they study. In this photoacoustic context, we define this term, and in case of RPC, we will study, or any different shapes, we will study how the differential scattering for photoacoustic cross section will vary with different angle. So you see, these are the three different shapes, and we have three different plots: blue for this, green for this, and red for this, and black line for a sphere. So black line because for a sphere we don't expect any variation. Cross section will be same from any direction. But this, and you see z axis is our theta equals to 0. That is the okay, and from that we count our theta, and pi by 2 is here. So this is the polar angle. And you see that we see a dip here, and it is appearing about 40 degree. But for stomatocyte, for diseased or damaged cells, they are appearing slightly earlier. So we submitted a paper here. Can you stop here? So